This is the last one in this module. Aren't you excited? I know I am. Kind of exciting. This is section 3B, putting numbers in perspective, and it starts out with a mistake. Isn't that great? It's all in this green mess. It's bad typing, sorry about that. When I was redoing the notes, it got all kind of jumbled up together, so we're going to do them out pretty for you. Where it's millions is actually equal to 10 to the 6th power. Billions is 10 to the 9th power, and trillions is 10 to the 12th power. It's convenient for you to have that memorized. Just wanted to let you know. We're going to talk a little bit about scientific notation. I'm hoping you have already learned that from somewhere else. But if you haven't, then it's my job to go over it just a smidge. So the rules for scientific notation state that any scientific notation number, which by the way, scientific notation started because scientists got really tired of writing all these great big numbers or a whole bunch of numbers for really small, insignificant number. So they use a whole bunch of numbers to represent a really tiny number, or a whole lot of numbers to represent a really large number, when they really didn't need all those numbers. So they came up with scientific notation where everything was rounded off into tens. Scientific notation became a really big thing, and it turned everything into the metric system, and things started gravitating towards the metric system. Turns out almost every country in the world follows the metric system now. There aren't but a few countries that are holdouts, and believe it or not, America is not one of them. America as a whole refuses to use the metric system. We don't like it, but it has been put into legislation probably 2 or 3 different times that we should use the metric system. Businesses have all converted to the metric system because they have to be international now, and every other country is using the metric system, so businesses are using it now. However, country as a whole just refuses to go, but that's okay. Scientific notation, however, is something different. It follows a rule where n is a regular number, but that regular number has to be between the number 1 and the number 10. It can be 1, it cannot be 10. And then you multiply that number by 10 to some power, where k is a power of 10, which tells us how many places it is. This k should actually be an exponent, so it's 10 to a power. So really it looks like n times 10 to a k power. Looks more like that. Numbers bigger than 1 or large numbers always have a power of 10. That doesn't make any sense, does it? Something's missing here. Just wanted you to know. Something must be missing in the notes. There were some notes issues in this section. Numbers bigger than 1 or large numbers always have a positive power of 10. Numbers smaller than 1, decimal values, always have a negative power of 10. Positive and negative, they need to be inserted in there. We missed some of my lines. Fill-in lines were absent in this section. I don't know what happened to them. The fill-in lines got obliterated on this page. I don't know. They are missing. I don't know what happened. I should probably go back and fix that sometime. Okay. Write each of the following numbers in scientific notation. So when you go to write a number in scientific notation, the first thing you have to do is figure out the significant digits. So the significant digits are digits that are not big groups of zeros. So when I look here, all of these numbers are significant. No long strings of zeros exist. When I look down at E, we have some long strings of zeros. See what I mean? So up here in A, no long strings of zeros. So they're all going to be significant digits. I need my decimal point to go behind the very first number. So I'm going to have 3 and then my decimal point. And then I keep writing all those significant digits. So I'm going to keep writing the 5, 7, 8. They all get written down. We don't ignore them. They stay there. Then times my 10. And then I need an exponent. My exponent is the number of times my decimal point had to move. Decimal point was originally here, behind the 8. Now it's here. That means it moved 3 times. Now the question is, did it make a bigger number or a smaller number? This is a bigger number. So when I multiply this smaller number times this number, I needed to make a bigger number. So this is going to have to be a big number. So I need this to be a positive 3, so it'll be a big number. I need this to be a big number to make this small number turn into a big number, so that'll be a big number. So this has to be a big number, so that's going to need to be a positive 3. That's how I know that this is a positive 3, and therefore that's the answer. Now there are some people who say, no, it needs to be a positive because it moved to the left or to the right, or it needs to be negative because it moved to the left or to the right. If you get into that, you're going to end up with issues about, well, no, if it's negative, then it's always this, or if it's positive, then it's always that. And you're going to end up making mistakes because you're going back and forth in 2 different directions. People get confused that way. Always think bigger and smaller instead of left and right. You'll make less mistakes. Here, you want the decimal point to be behind the first digit. So I do my 9.8435 times 10. And then how many places did my decimal have to move? It moved twice. I went from a smaller number here to a bigger number here, so this is going to have to be a bigger number. So it needs to be larger, not negative. Here, I have a string of zeros. I need my first number to be a 5 because I don't want to write down the string of zeros. It's the whole point of scientific notation not to have to write those zeros. So 5.8 times 10, and then the point ended up here. I have to move my decimal 1, 2, 3 places. I ended up with a bigger number here, and it's got to turn into a smaller number, so I need this to be teeny tiny. That's why it's negative. It's got to be a mighty small number if I'm going to multiply this big number times the small number to get a small number. Whatever this is generally what you want that to be. I did 3. You do 3. These will be located in Blackboard, just like we did a couple of sections ago. You'll be able to find them. Scientific notation into ordinary notation. If the exponent is positive, hey look. Move the decimal to the wow. This is even written poorly. They dropped the exponents. Oh, that looks horrible. Oh, this is so bad. Oh my goodness. I'll have to rewrite it. So this should be 9 times 10 to the 7th. 1.1 times 10 to the 3rd. 2.3 times 10 to the negative 3. These are the problems. 4 times 10 to the negative 6. 1.3, oh sorry, 1.8. 1.23 times 10 to the 8th, and then 2.34 times 10 to the negative 2. Those are the problems. Convert each of the following numbers from scientific to ordinary notation and write its name. I don't care about you writing its name. My math lab will tell you to write its name too, but I think they give you a choice. You don't actually type out its name, you pick it from a list. Excuse me. So, if the exponent is positive, you have to move the decimal. In other words, you're going to want it to be if the exponent is positive, you're going to want it to be a really big number. So you're going to have to move the decimal to the right to make it a big number. To the right. And I'm going to add to make it a big number. And fill in with zeros. And here you're going to move the decimal to the left to make it a small number. And fill in with the empty gaps. Fill in with zeros. Convert each of the following numbers from scientific to ordinary notation and write its name. So here when you have 9 times 10 to the 7th, start out with the 9. 10 to the 7th, we need, our decimal point is here. We need to move it 7 places. 1, 2, 3, 4, 5, 6, 7. That's 7 places. $90 million. Here you would move the decimal point 3 places. $1,100. Here you're going to have to move the decimal point back 3 places. So you have 0.0023. I did the first 3. You do the second 3. They're also on Blackboard. Look at that. I like how that works. It does make for a quicker video. though. I mean, you know, we could have spent a lot of time on this. But, I mean, we spent enough time having me rewrite stuff, I thought. Rewrite the following statements using a number in scientific notation. The number of different 8-character passwords that can be made with 26 letters and 10 numerals is approximately 2.8 trillion. 2.8 is already written for our first number. Trillion, we already know, is 10 to the 12th. So that would be our scientific notation. Rewrite the following statements using a number in scientific notation. A large power plant generates 2.2 gigawatts of electrical power. Recall that a giga means billion. So 2.2 is already written for our first number. Times billion, we said, was 10 to the 9th power. Oh, this one. Oh. There were approximately 2.1 million marriages in the United States in 2019. Express this quantity in marriages per hour. 2.1 million. Now I could write that in scientific notation, but that's not going to help me express it in marriages per hour. I'm going to have to write 2.1 million as a number. So when I write 2.1 million, instead of me writing 2.1 million, I need to write that out as a number. And the trick is putting the comma for million where the decimal point is. So it's like 2,100,000. That's my 2.1 million. That's what it looks like. In marriages is what's on top. Per hour. So that's for 1 hour. They want to know, no, sorry, this is in 2019. So that's per year. That was for 1 year. They want to know per hour. So I'm going to have to change it from years to hours. What do we know about years? Well, 1 year is 365 days. What do we know about days? 1 day is 24 hours. So my years can cancel out, my days can cancel out. This gives me marriages per hour. That's good. So I can multiply across the top and divide by the bottom, and that gives me 239.7 marriages per hour in our country. Americans spent approximately 1.7 trillion on food in 2019. Express this amount in dollars per person. 1.7 trillion. So it starts out as 1.7. So that's 1,700,000,000,000 million thousand okay, that's what that looks like, over our 330 million. I could cut out some zeros. So these 3 zeros can cancel out with those 3 zeros. That works. These 3 zeros can cancel out with those 3 zeros. That works. This 1 0 can cancel out with that 1 0. That works. Now I'm just dividing the top number by the bottom number, which looks like to me it's 170000 divided by 33, which is a lot easier to stick into a calculator. When you do that, you get that each person is spending $5,151.52 on food a year. Wow. In 2020, the present population in the United States was approximately 2.3 million. How many stadiums with capacity of 60,000 would this population fill? The annual U.S. emissions of carbon dioxide were estimated to be 5.3 billion metric tons in 2020. Express this quantity in per capita terms, assume the U.S. population of 330 million. Per capita terms means per person. Do 7 and 8, and they will also be in Blackboard. We're going to do 9 now, because it's a little different. Not a lot different, but a little different. The universe is estimated to be about 14 billion years old. Billion, million, thousand, there we go. 14 billion years old. What is its age in seconds? That's years. 1 year has 365 days. Whoops, 65 days. 1 day has 24 hours. 1 hour has 60 minutes. And 1 minute has 60 seconds. Now I know all that makes sense to you. All we have to do is multiply them all together. Your calculator would have a problem with all that. You'd have a problem being able to read that answer. Let me tell you what you could do though. You could take your handy dandy calculator and work your way backwards. You could say, instead of us starting with this great big number, let's instead start with the 60 and say 60 times 60 times 24 times 365, because your calculator can do that number. And then instead of multiplying it times this great big number, just multiply it times 14. When you do that, you're going to get 441,504,000. This is not the answer. This is just the answer times 14. We left out all those zeros, right? But just like before, when we could cancel out zeros, we're going to do the same thing, only this time I left them out, so now I'm just going to add them back in. So now I'm going to add in 0, 0, 0, 0, 0, 0, 0, 0, 0, because that's what it would have done. And this is what our answer would be. Now I don't fancy looking up what that number would really be called. I don't care what it would really be called. Doesn't really matter to me what anything to the 21st spot is called. But I can write it in scientific notation. 4.41504 times 10, and then how many spaces did our decimal point have to move? That's right. It moved 20 places. So this is a lot easier way of writing that number than writing that number. Just saying. That's a reason why we would want to use scientific notation. Questions, problems, concerns? You probably are going to be getting ready for a module test of some sort. So make that happen. Make sure you've done all your homework, all your module homework. If you have questions, please let me know. Don't feel scared to email me at any point in time. I'm happy to answer emails. Let me know if you have any questions or concerns. Have a lovely day. Bye.